I didn't put it. I'm gonna bring it for something and every day.
So I think we already talked about the money hall problem, right, the first day? Talked about the doors and all that kind of stuff.
Yeah.
And we did the birthday thing, right, just to show you. And really the reason I do those two things is to show you how the brain is not hardwired to understand probability coming into the world, right? We're kind of hardwired to pick up language. It's part of the evolution. I'm not going to get into that whole thing, but as far as understanding probability, we are not hardwired. We made it all up so that we could talk about things. My little brother gives me some shit about talking while I'm talking. There you go.
Oh, sorry.
About the fact that I teach probability, and he says, Jeff, what the hell? Everything's 50-50. Either it happens or it don't. I'm like, dude, do not become a doctor. What the hell? You know, doc, what's my chances? 50-50? No, that's not a good scene. I don't want to hear that shit going into surgery, right? So obviously there's a problem with that thought, but the way he's looking at it is the way that some people kind of look at it and get it wrong. They look at it after the fact. Something had to happen. It was either this or this. But that's not useful. It's not good for planning. Like today, there's a 30% chance of rain. Now it happens to be later tonight, but that kind of would help you figure out how to dress or what to bring, right? Now, of course, in this area, even when they say 100%, it might not rain at all, but at least you kind of bring what you need to in case. So there are reasons for probabilities. I have to know how they work and how to interpret what they mean. So for example, if I said, I flip a coin, what's the chances I get a head? What are the chances? 50%. Now that is a 50%. Why? Why is that a 50%? There's only two options, and we're all assuming that the coin hasn't been weighted somehow. So you can actually weight the coin so that it comes out a certain way more often, right? So let's assume it's a fair coin. They have equal chances of happening. That's the one time it would be 50%. We all good? What the hell does that mean, though? That doesn't mean shit for a single flip. I'm not going to get half of a head on it. Whoop, half a head. It splits in half. Like, I got to stop doing that. Do you guys understand what's happening? So what the hell does it mean then? What is that 50% chance of getting a head on a flip of a coin? What does it mean? What does it mean?
It means when you do a lot of flips for a long time.
There it is.
When you do a lot of flips for a long time, it'll start looking like you get them about 50%.
I love it. That's the real interpretation of probability. So that means in the long run, if I flip the coin 1,000 times, number one, I'm a little worried about my life, but number two, I'd expect to get 50% heads. And it's kind of like the law of averages. You ever heard of law of averages? The law of averages kind of butts heads with Murphy's Law. Have you guys ever heard of Murphy's Law? You might never have heard of it, but you live it every day. Who knows Murphy's Law? Anybody know Murphy's Law? You guys are funny.
No.
Oh my God, you live it every day. Yes? No. If it can go wrong, it will go wrong. So it's a very negative way of looking at things, but man. So the law of averages says if you get a red light, you should get kind of like, it should balance out the red lights you get and the green lights you get. And normally from a human perspective, we notice the bad stuff more, so we feel like, I'm getting a lot more freaking reds trying to get in. Right? Control that. A little rage. Okay. How are you feeling so far? I mean, I haven't really done anything technical yet, right? But it's just, it's good to understand what it means when somebody says so if somebody said, I have a 20% chance of surviving some surgery, what does that mean? I interpret it the same way. If that surgeon did that surgery a lot, 20% of the time it would be successful. Yeah. Yes. But it's good to know what it means, right? Okay, I'm with you. I didn't say it was good. I just said good to know what it means. Okay, so let's do some more. I want to see what you guys kind of already know to a point. Let's do like the traditional classic. Let me change it up a little bit. Let's say I put 12 crickets, 8 grasshoppers, and let's make it different, 9 beetles into a bag. Right, we normally put poker chips or something boring in there. Let's put some living shit in there. You're going fishing. right? This is all in this bag, and I reach in and I pick out one of the bugs. What's the probability that that bug is a cricket? What is the probability that it's a cricket?
12 out of 29.
12, yeah, exactly. 12 out of 29. Now, think about this. Don't write this down. What do you say to the person that writes 1 out of 12? How do you think they're looking at it if somebody put down 1 out of 12? How are they looking at it? Incorrectly. Why is 12 out of 29 the right way to look at it? Because you have 12 crickets, 12 chances to get what you want out of 29 total things that could happen. So 12 out of 29 of the time, you'll get a cricket. So if the person puts down 1 out of 12, which I get all the damn time, I can understand where they're coming from, but can you guys figure out what the way they might be looking at it? Yeah, this is sort of like saying, what's the chances you get your favorite cricket if you got a cricket? Oh, where's little Darla? Oh, so there would be one chance. So this would be if I get a cricket. If I do get a cricket, what's the probability it's a certain cricket? That would be this. There's only 12 things that could happen then, because I just said it's a cricket. What's the chance you get your favorite little cricket? I ain't questioning why it's your favorite little cricket. You have your own reasons. There'd be 1 out of 12 chance. So probability, the basic idea of probability never changes. It's always how many things match what I'm looking for divided by the total things that could happen. That's how you set up the ratio for a probability. You guys semi with me? Okay, I like it. So what's the probability I get a bug or a grasshopper? A board, I like that.
9 out of 29.
Resistance is futile. Say
9
again?
out of 29.
No.
Yeah, a beetle or a grasshopper. So how many things match what I'm looking for? Well, 17, because I'm going to take a beetle or a grasshopper, right? I'm happy with either one. Out of 29. I like it. Okay. So that's the real basic probability. You have got to be able to do that coming in, basically. You should know that. Okay, I like it. So let's step it up. Let's see the next kind of level of stuff. Why? Because you're going to have to anyway. Okay. So one way I like to give you data for probability is in a table. It's called a contingency table. So, for example, if I asked some people a question, let's put this as yes, sorry. Yes, no, maybe. Right? Because I'm not feeling very creative, I'll let you figure out what the question might have been. Let's say 3, 12, 7, 18, 1, 3. I like it. What if anybody's got some good possibilities for what the question might have been? I don't know. Okay. Now, when I give a problem, I give these blank exterior boxes because any question I can ask you about probability, the bottom is always going to be the total that could happen, right? So I need to get all the totals involved with this problem. So how many, let me see if you guys can read this correctly. How many people said yes?
21.
I like it. So 21 people said yes, because that's the yes column. You guys with me? I always get somebody that looks at it the wrong kind of way. But this is the yes columns. There are 21 yeses. How many no's?
13.
Crazy. How many maybes? 10. How many men? 22. How many women? 22. Look at me being all equal.
44.
Yeah. And what do you think happened to this person? Why did they put an 88 there? They added these people to these people, but these people are these people. What the hell? Don't count everybody twice, right? Okay, you guys with me? So nice thing is that's 44, and then you just kind of double check. This better add up to be 44 also, and it does. Thank God. So I got everybody. I like it. And don't worry, when I do a problem like this, and I'm going to have like A through G or something, these questions based off of this. If you make a mistake here, I take points off once. And then as long as you set everything up correctly, you're not going to lose points again. So if you accidentally said 42 here or something silly, because your brain just took a little vacation, then I'm only going to take points off once. As long as you set these up correctly, I'll be okay. All right? Okay, I like it. So here, let's start off with a nice question. What's probably that if I pick somebody at random, I pick a woman? Careful. How many match what I'm looking for? 22. And how many total things could I have picked? 44. In this case, they're people.
And you could, what, make it smaller.
And that's exactly half. So 50%. I like it. Now, just so you know, this is the work. So if you just give me the answer and I don't see the work and you get this wrong, you're going to lose all the points because I have no way of knowing what the hell happened. So this ratio is the work. And then after that, you can leave it as a decimal. You can make a percentage. We're going to make that a little more concrete later. If you want to kind of get used to what we're going to be doing later in the semester, we're going to do 4 decimals. We'll see why that's true later. Yes, sir?
So anytime we're working with probability, you want to convert it to a percent?
Well, we make it percentages normally because that's what we're used to dealing with. And we made percentages because they make sense to us more immediately. If I say 0.03, I'm like, what the shit? And you say 3%, oh, okay, 3%. I like it, I like it. So part B, let's do, what's the probability that I get somebody who, all right, let's try this one. A man, or they said no. Nope, careful. You got ahead of me, that would be and. They have to be a man, or they said no. So I want to include all the men, right?
23, 12, 35.
So I hear people saying 35. The problem with that is you counted some people twice. Do you see that? If I count all the men and I count all the no's,
13.
I counted them twice, didn't I? So what you can do is you either can do 22 plus 13, but then you have to subtract 12 out of 44, right? Or to be smart, you can just go 22 plus that one I didn't count yet, because what's 13 minus 12? The one you didn't count yet, right? Let me stop there for a second. It's not fair to count anybody twice, right? Like in an election, if your neighbor got 2 votes and you got 1, I think you'd be upset. Like, what? Who else got 2? What? No. Yes?
So we're always going to do the one in the first position first? Like you wouldn't be able to count the no's first?
No, of course you could. You could also do, it would be the same thing, wouldn't it? Be 13 plus 22, you'd still subtract 12. Right? It doesn't really matter. Or I could do 13 plus the 10 I left out. Is that what you're asking? As long as you take one of them plus whoever you left out.
Okay.
I like it. So you could also do just 22. Where do you go? Yeah, I could do 22 plus 1. Or I could do 13 plus 10. All of those is what? All of those come out to be 23 on the top. I like it. Do you guys see what on the top, what am I doing? I'm gathering everything that matches what I'm looking for. I can take these people or these people. So let me give you my little spiel about or. Or is the nice bouncer. Or is the bouncer that says you can only get in the club if you got a lot of money. I'm a teacher. If you dress nice. No. Got a nice car. No. Or, Joe, I know Joe, hey Joe, and then I get in. Because he said or. He said or, didn't he? So I just have to do any of those things that I'm in. So or always makes the numbers bigger because it allows for more possibilities. And is the next one we're going to do. And is the evil bouncer. You guys, how many of you guys have ever applied for a scholarship? looked at like okay. Nowadays you can go online and there's actually like an application for applications now. It's insane. Back in my day, we had to go to the financial aid office and they had a book like this big that would be updated every couple months or something stupid. Yeah, this is before, Al Gore invented the internet. And then you'd have to flip it open and I go, you gotta be a math major. Yes. And you have to have a greater than this GPA. Barely. And you have to be blah, blah. And I'm like, yes. And you have to be a woman. Shit. Let's put that first. I mean, that actually is a true story, to be honest. I mean, there was one, I'm like, yeah. Oh, you gotta be, okay, shit. All right. So, and is mean. And says you gotta do this. And you got, automatically have decreased the number of people that it could be. So if I said, okay, the people, I'm going to take a few people with me. We're going to go get ice cream. You have to be a man. Oh, that's so mean, Jeff. And you have to be wearing a hat. So I only see a couple people that'd be able to go. 3. Hey, look at it. And somebody else is like, shit, man. And that was hypothetical. Don't get all hopeful for ice cream. Ain't going to happen. All right. So or is the nice bouncer. It always makes the top number bigger. And is the mean bouncer because it has more and more restrictions on things. So let's try an and problem out. What is this, by the way? 23 out of 44?
52%.
Yeah, 522.
7.
7? I like it. So 52.27%? I like it. So what about, let's probably get a woman and they said maybe. What do you think? 3 out of 44. Thank God. Don't stop at 3 because the probability cannot be bigger than what? 1. Because 1 means 100%. And I know psychologically you can give 110%. Sure. Can't do it anymore. Yes, you can. You can do it, right? But mathematically, that's bullshit. Right? So please, dear God, if you do get an answer, you don't see why it's 1.2, don't just stop. Say, I know it shouldn't be 1.2. Say something, because otherwise I'm worried about you. So yeah, this will be 3 out of 44. Which is something or other. 0681? Okay. I like it. How you guys feeling so far? I mean, you guys with me? It's kind of nice. You keep that little idea of or is the nice bouncer. Makes things bigger, makes more people come in. So you can kind of, after you do an or problem, you just make sure it makes sense. If an or problem, you get 1 out of something, you're probably wrong. It should include more possibilities. All right, so let's try. What is the probability that I get somebody who said no, given they're a woman? So what is it that I know about the person? Now, let me say it again. Listen to me. The probability that the person said no. The probability that the person said no, given that they're a woman. It's not the same thing as and. In a rough way it is, but you'll see what it is. Yeah, what do I know about the person? They're a woman. So what's going to go on the bottom now? 22. And now, out of those women, how many said no? Because, why do I exclude the men? Because I know it's a freaking woman. So then you can pretty much just do this, right? So out of 22, how many said no? 1. And then whatever the hell that is. 045. Every now and again, I give you some shit. All right. So I'm laying the groundwork. What we basically just did, we haven't gotten into the real nitty-gritty yet, but we basically just covered almost every section in chapter 3. There's one section on and or. There's one section on given. There's another section that we haven't done yet, but is coming. Okay, I like it. So let's really analyze this last guy, and then we're going to analyze this part B. Let's do one more of these, and then we'll really get a feel for what's going on. What's the probability that somebody is a man given that they said maybe? There it is. I was waiting. What do you know about the person? They said maybe, because this says probability they're a dude. I have no idea if they're a dude. Not the probability they're a man, given that they said maybe. So there's always that second one that tells me what the bottom's going to be, because that's the thing I know. So given they said maybe, so how many people am I talking about? 10. Out of those people, how many are men? 7. And that's a nice one to do. 70%. What?
Wait 10.
So what do I know about the person? Given that they said maybe.
Mm-hmm.
And how many people said maybe? 10. So I know they said maybe. So how many people could it be? 10 people it could be. Out of those people, how many match what I'm looking for? 7.
So after given is your denominator.
Yes, exactly. Whatever this is sets up what your denominator is going to be, because that's the total number of things it could be. Why was it 44 here? Because I don't know shit about the person. It could be any of the 44 people.
But how come for the that was 22 for
Because what am I given here? That they're a woman. And how many are women? 22. Do you see that? So whatever I'm given that they're a woman. So who am I going to focus on? The women. How many women are there? 22. It can only be any of those people. So it's got to be out of 22. Here, given that they said maybe, it can only be out of those 10 people that said maybe. I'm basically throwing the other people out. Yes, sir.
So given shrinks the population to what follows?
Given shrinks the denominator down. Yes. It's going to focus your attention on a subgroup of the whole original group. I like it. We do givens all the time. So I'm like, given that it's 3:30, I'm going to sit here for a while and wait until the traffic is done, depending on which way I'm going. Right? We do. These are called conditional probabilities. That makes so much sense because the given is the condition. Under the condition that this happened, then the probability that becomes this. What was the probability it was a dude in the first place? This is just a man. It's probably just a man. 22 out of 44, 50%, right? I really want to make this clear right now, because we're going to talk about this a few more times. This is the one that everybody mixes up, and I just wish you wouldn't, because it isn't that hard. Probably a dude is 50%. There's a 50% chance it's a dude. If I know that that person said maybe, does the probability it's a dude change? What's the probability maybe? 70% now, right? And what was the probability of a dude before? 50. Are those numbers different?
Yeah.
Yes. So let me ask it again. If I know the person said maybe, does the probability they're a dude change from what it was? Yes. There it is. Knowing that they said maybe changes the probability they're a dude. Therefore, we would call them dependent events. Bless you.
Thank you.
Right? Dependent events. If they didn't change, they would be independent events. Does this one care whether they said maybe or not? Yes, because if they did, the probability shoots up. Right? It's sort of like if I saw, and I love how people react to this, well, if I saw somebody in the distance and they were too far away and they had kind of long hair, I can't tell if it's a man or a woman. Right? They're so far away. I don't know. And they're wearing sort of something that could be either way. So what's the probability it's a man? 50%, right? Roughly. Now, what if I just seconds before saw them get off of a Harley-Davidson motorcycle? Is the probability of the man still 50, or is it higher than that or lower than that?
Higher.
It's higher. Now, I love it. One semester, somebody got really upset. Some girl said, no, girls drive. And I'm like, when did I ever say they don't? This is where people get offended at the wrong time. It's just numbers. more men than women do, right? So the probability goes up. That doesn't mean that no women drive freaking motorcycles. It just means the probabilities change. And I still have people look at me like they want to hit me, but oh well, too bad. You can't do it. Bring it.
It is what it is.
Yeah, I don't know what else to do. So it's just the idea of probabilities. It's sort of like, okay, given that you eat cheesy poos for breakfast every morning, what's the probability you're going to die early? It kind of goes up, right? No,
We're still alive.
cheesy poos. All right. All right. Oh yeah. So let's focus. Let's focus on two things up here. Let's focus on these givens, and then the or. I want to actually make some formulas up. Now notice something. Did I give you any formulas for this? No, we didn't use a damn formula. Probabilities, if I can count everything involved, then I'm not going to use a formula, because the idea of probability is all about the number of things. If I give you a problem where I don't give you any of this, I just say the probability of A is 0.7 and the probability of B is 0.4, and what, find out the probability, then you've got to plug it into formulas. It's the people that try to do this problem with formulas, they try to force it to work. No, you got to be careful with how you do that. But now let's figure out what the formulas are. Let's see. Let's do or first. So let's kind of analyze this guy here. What was 22 out of 44? So this is man or no. What did 22 out of 44 relate to? Man. So it's probably a man. Plus, what was 13 out of 44? The no's. So I added all the men to the no's, and we know now the problem with that was there were some men who said no, so they got to be counted twice. So what's 12? Yeah, so what's the key word I want to use? That's the men, they were a man, and they said no. So minus the probability of man and no. Okay, so here's the formula for or, the official formula for or. If I have probability of A or B, and A and B could be any event. The capital letters are sort of like the variables for statistics, for events. A could be roll a 7, and B could be fall out of a plane. You add the two together, but then you better subtract off any that are both, because you counted those twice. So or is basically add, because or increases the probability you're going to find what you're looking for. It increases the chances. It increases what you're looking for. So what about given? So probably A given B. Oh, this is the sign for given, by the way. This always throws people off, but I'm just not going to be able to stop myself. This is not division. This is a straight up and down line. It means given. A given B. So you know B happened, and what's the probability of A now? Did it change? Okay. So over here, when I did no given woman, what went on the bottom? The number of women, right? Because that's what I know is happening. And what went on the top, not knows, what went on the top? Somebody mentioned it earlier. Woman who said no. So they were a woman and they said no. So it kind of makes sense if you know that B happened. Let me give you a picture here. I don't know if you've ever seen these little Venn diagrams before. If I know that B happened, something in B happened, what's the only way that it could have happened in A also? Is if it's here. But what is this? This is A and B. This little section, this little intersection here is A and B. So that is the next little formula. Some of you guys might be wondering, you did or, why didn't you do and? Because and I can do now. Notice how and is in this formula. So I can actually figure out the formula for and now that I've got it showing up somewhere. So So or is basically add, and is going to become basically multiply. Let me, before I even show you the algebra, let me make sure that it makes sense this is true. If you live in a really bad part of town, how many locks are you going to have in your door? Yeah, probably more than one, right? Yeah, I'm not talking about all the other possible defenses you could set up. How many dogs do you own, or at least a recording of a dog that'll turn on if somebody comes up? But I'm just talking about the locks in your door for right now. Let's not get into all the other stuff. Everybody with me? Why do you have more than one lock? Well, so what's wrong with one lock?
Easy to get in.
Why is that easy to get into? What do you mean?
It takes less time.
All right, well, number one, it takes less time, but you're actually hoping that that's more than just taking up their time. You normally have different types of locks, right? Yes. So it decreases the probability that they will get in. Or, let me think. So there's no way then that, let's say that one lock has let's say a 0.1 chance, let's say 0.1% chance that somebody's going to pick it and get in. I'd hope to God that if I put some other lock on here, that's not going to make it add and become 0.2. I can't do it the same way I do OR because the probability shouldn't go up. It should go down. Remember, what does OR do? Let's more and more people in. That's not what I want to do in this case. I want AND to decrease. I want it to get smaller, right? Well, how can they get in the door? They have to pick this lock and this lock. And can't mean add then, because then if I put more locks, it's increasing the chances of getting in. That doesn't make any damn sense. So the weird thing with numbers that are between 0 and 1, when you multiply them, the result gets smaller. Like what's 1/2 times 1/2? 1/4. That has gotten smaller. Are you with me? All right. So that's one way of seeing. So if I put one lock and then another lock, I multiply those together to see what the chances are. Now this is maybe let me see if you guys know this. What would this be as a decimal? Oh, you got to be able to do this. How do I go from percent to decimal? Yeah, you move the decimal back once, twice. So 0.0001. Yeah. 0.001. And then what about this one? The same thing? Why is it 2 times? Because percent means per 100, right? That's where the word cent comes from that we use for cents. So what would this be? This is 1 out of 1,000 times 1 out of 1,000, if you want to look at it that way, which would be 1 over 1,000, 1 over 1,000,000 chance that they'll get in. So that's pretty good. I can live with it. Another situation would be if you had a really important test in the morning. Do you guys have alarm clocks or use your phone, right? If I have a really important thing to be up to, like really crazy important, right? I'm going to have a couple things, right? And I'm probably going to have a friend call me, and I'm going to something, right? I'm going to have several things. Why do I do that? To decrease the probability that I don't wake up. Same idea with the locks. I like it. Okay, so it should make sense that the formula should involve multiplication so that it makes all the probabilities get smaller. Because what is and? And is the mean bouncer. How many people get in the club? Less and less and less, because you got to do all these things. The or bouncer, you could do any of them. Come on in, right? I don't know why he's vaguely Irish, but I don't know. Okay, so let's look at the given. I'm sorry. Yeah, let's start with the given, and then we'll make the and. So here's the given, dude. So tiny little bit of algebra. How do I solve that for the and statement? Alternately, you can think, how do I solve this for x? Okay, so how do I solve that for the dude on the top? Multiply by the dude on the bottom. I like it. So I'm going to multiply that up, and I get probably of a and b equals probably of b times probably of a given b. Stay with me. Now again, there's no way in hell I'm doing all that freaking work if I have a table with all the numbers looking at me. We did an and problem already, didn't we? Now, if we did all this work and we did it correctly for the table I had up earlier, it's going to come out to the right answer. So a formula is not always the best way to do something. I don't care what anybody ever told you, right? It isn't. It's just the only way to accurately capture the idea in general. But sometimes for specific problems, there are easier ways to do it. So if I give you something to count, if I were you, I wouldn't use the formulas at all. I would just count what I need and put them over what I need, and I'll be done with it. Okay. So I have examples. So I have like a probability worksheet that we'll do in class. I have a practice quiz that I'll have an answer key to. It's insane. So I'm going to try to get you guys ready. Let's see. Let's do a problem with this that's a little different from what we've already done. Yes?
What does and mean again? Add or multiply?
And?
Yeah.
So or is basically add.
Add.
And is staring in the face.
Multiply.
Multiply. Yeah. Or means basically add. Why do I say basically? Because see that it has a little adjustment? And means basically multiply. Why do I say basically? Because this isn't probably B times probably of A, is it? It's probably B times probably of A given B. So let me show you another way to look at this that makes it make even more sense why it should be this way. Do you guys, how well do you know cards? Anybody not know cards at all? Like, I mean the basics. I don't mean let's sit down and play some, yeah, no, we're not going to do that. Right? How well do you know cards? How many suits in a deck of cards? 4. Okay, so let me build this up a little bit here. Some of you guys got excited. Are we playing for money or are we playing for cookies? So cards, there's 4 suits. What are the suits? Sounds like Lucky Charms. We got hearts, diamonds, blue clovers, spades. Oh, Shisa. How do I draw a spade? I've already forgotten. It's like basically an up, down, down heart. Oh, that's horrible. Let me just write spades. Look like a butt. This is true. And clubs. Okay. So there's 4 suits. How many total cards? 52. Right? There's a really fun game. 52 card pickup. Yeah. If you have an older brother or sister, you might have played that a few times against your will. So 52 total cards. So how many cards in each suit? 52 divided by 4. It goes in evenly, thank God. It would be weird if we had more hearts than something else. Anybody know how many? All right, let's think about it. There's ace. Let's count aces low. Ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 is Jack, Queen, King. That's 1 through 13. There's 13 cards in each suit. You guys are all like, is he going to teach us how to cheat at 21? No. Watch that movie yourself. Can't do it anymore anyway. Okay. So these are beautiful for questions like this. So let's get us started. So if I pick one card, let's just go back to, this is really, really basic. Let's probably get a king. Yeah, how many kings? There's one, a king of hearts, king of diamonds, so forth, right? So there's 4 kings out of 52 cards. Because what could happen? 52 things could happen. Out of those, how many match what I'm looking for? 4. Don't say 1 out of 4. I didn't say if you get a king, what's the chances it's your favorite king? I didn't say that. Okay. Now, so see how I picked one card. Right? Now, things get, of course, more interesting when I start picking multiple things. So let's say I pick 2 cards with replacement. What's that mean? Well, that means I pick a card, I look at it, and I put it back. And then I pick another card. Can you guys see the difference? If I would have picked a card and threw it away, what changes? 51. The denominator changes. So right now, the denominator is not going to change. All right, denominator. So what if I pick 2 cards? What's the probability you got a king and then an 8? What's probably the first card is a king? 4 to 52. Now I'm going to use this formula. Look, this is the end. All right. Why do I need to use a formula? Because I can't just count all the possible pairs, because that's a lot. I can't just count that, or I don't want to, and I don't blame you if you don't want to either. So let me just multiply by, now, so what's this part going to be? The probability is an 8. The next one's an 8, given that I picked a king. But what did I just do with that first card? Put it back in. So given that I picked a king, nothing changes because I put it back in. What's probably getting an 8 now? How many 8s? 4 out of 52, because I put the first card back in. Are you guys with me? So with replacement doesn't change anything. It keeps things independent. It doesn't change anything. So this will still be another 4 to 52, which is 1 out of 169, which is whatever the shit that is. I have no idea. As far as I can get. You guys like, what the hell? 1 out of 13, 1 out of 13, 1 out of 169. Somebody could help me, but nobody wants to. Okay.
So you just multiply it.
Yeah, if you want to, you can just do 4 divided by 52 times 4 divided by 52 in your calculator. Get out a decimal, that is
0.00591.
0.00591.
591.
Ooh, yeah.
You want us to round it up, or you want us to keep like that?
That's fine.
That's fine.
Yeah. 4 places is good, but 1 more place is fine.
What do you mean by 8? Like 8 times?
An 8. An 8.
Oh.
Got a king and then an 8.
Oh, no.
I like it. All right. So the 8's not a number really, it's just the name of a card.
Yeah.
Yes.
You said replacement means it's independent, right?
Yes. Because nothing, it doesn't change then. Nothing, the bottoms stay the same. It doesn't alter the probabilities. All the probabilities stay the way they were because it kind of resets. So let's do that same problem, but this time I pick a card and feed it to my little brother. What's going to happen then? If I do the same problem, but now I pick 2 cards and I don't replace. So now it's going to be probably a king and then an 8. Would be 452 for the king because I haven't done a damn thing yet. Feed that. Now how many cards have I picked? 1. So what's the most that the next probability can change by? 1. I always get people that change it by 4. I didn't pick all 4 kings, and that would be a cool trick. Shuffle. 1, 2, 3, 4. Hey. No, I'm not that good with these cards. But now how many 8s are left? Still 4, because I didn't pick an 8. But how many cards are left? 51. I like it. And so we're going to help me out. Somebody's help me out.
Do what?
Help me do that.
0060.
0060?
Yeah.
See how it went up a little tiny bit? Why did it go up a little bit? Because the chances of an 8 now went up a little bit because they got rid of a card that's not an 8. Do you guys see that? That's why it changed a little bit. I like it. So this is not independent. This is dependent because the probability of an 8 changed. It used to be 4 out of 52. Now it's 4 out of 51. It changed.
So and is dependent?
Careful. No. So when I replace stuff, the ands are, this kind of problem would be independent. It doesn't change any probabilities. If I replace it, everything resets. It's the fact that here I did not replace. That's what made this dependent. This probability changed from what it normally is. I like it. Let's do one more with this. So let's say I pick 2 cards and I don't replace. What's the probability I get 2 kings?
Without replacement?
Yeah, without replacement. Same idea. Yeah, so what I normally do is I put 2 empty spots, like a hangman game almost, because I have 2 choices, 2 picks I'm going to make. The probability of the first pick times the probability of the second pick. Well, the first pick of a king is still going to be... Now, how many kings are there? 3, because I threw that first king away. And people are always like, how do you know you got a king? I don't. This is all the probability that this happens. So the probability that a king is this times, assuming I got a king, what's the probability I get another king, right? I like it. So now this is going to become 3 out of 51. Now if you play any poker at all, you figure out pot odds. This kind of comes into play with what you can see on the table. You'd think I'd be really good at poker. I know the logic of it. I could maybe do online, but every emotion I have is on my face immediately. So it's like, anytime I ever played cards, I have nothing. No, doesn't work. And what's this come out to be? Say again, sorry?
0.0045.
4 or 5?
Yeah.
So that went way down. That probably went way down because I lost what I wanted on the next go. So the probability I got a king on the next pick went way down. I lost one of the kings. All right. So what if I picked 3 cards? I would just have another place times another one. 3 kings, it would have been times 2 out of 50. That's not difficult, is it? Not. And again, you can see the form of the idea of the formula of and. The first dude stays the same because nothing's happened yet. But the second dude might change if it's affected by what's already happened. I like it. Okay, all right. So, let me see. Maybe I can shut up for a little bit. Wouldn't that be nice? I want you to try out number 1 and 2 on this. We haven't really done enough for number 3 yet. But I do want to shut up for a little while. I feel like I've been talking forever. You guys probably feel the same. You'll notice that one side says this side in class. That means that's the one we're looking at right now. If you want to work with other people, you can. Just the first 2 problems.